All right, let's jump right into this explainer. We're going to completely demystify calculus today by reverse engineering derivatives and really exploring the sheer power of differentials. You know, if you've ever felt like calculus is just this cruel series of arbitrary rules you have to memorize, well, you are definitely not alone. But today, we're going to look at it as a deeply logical, interconnected system. We're going to see how derivatives and antiderivatives are literally two sides of the exact same coin, and how a simple change in notation totally revolutionized math forever. So, here is our roadmap for today. We're starting with the calculus undo button, then we'll uncover the ambiguity of constant C, explore the power of differentials, see how they make substitution incredibly simple, and finally, we'll bridge area and distance.
Okay, part 1, the calculus undo button, reversing the derivative. We're starting with a super basic question. If we know how to break a function down, how on earth do we build it back up?
You've probably spent a ton of time taking a function and finding its exact rate of change, its derivative. But what if we get the rate of change first? Well, look at the inverse relationship here. The derivative of x cubed is 3x squared, right? We know that. But then the integral sign acts as our ultimate calculus undo button. The integral of 3x squared dx takes us right back to x cubed. Integration is basically just the process of reading all of our differentiation formulas in reverse. And that is absolutely crucial. Right from the jump, we are just reading known formulas backward. If differentiation breaks a physical process down to see how fast it's changing at any given millisecond, anti-differentiation accumulates all those tiny instantaneous changes to figure out exactly where the whole process started. But, as you might have guessed, working backward does introduce a slight complication.
Which brings us to part 2, the ambiguity of constant C and dealing with missing information.
Whenever you evaluate an indefinite integral, you're pretty much forced to add this totally arbitrary letter C at the end. We've all done it. But what does it actually mean? Why can't we just lock down one single definitive answer when we reverse a derivative?
Well, it comes down to the geometric reality of what's happening. Think about it. The derivative of any constant number is literally 0. So the derivative of x cubed plus 5 is 3x squared. But the derivative of x cubed minus 100 is also 3x squared. If all we know is that the rate of change is 3x squared, we have absolutely no idea what that original constant was. Taking an antiderivative always leaves us with this vertical ambiguity on our graph. We're not finding a single curve, we're actually finding an infinite family of parallel curves, all with the exact same shape, just shifted up or down the y-axis. So this brings up the idea of uniqueness up to a constant. If two functions have the exact same rate of change everywhere, they are, for all practical purposes, the exact same function, just shifted vertically by some constant c. Adding and subtracting constants is literally the only flexibility we have when finding different antiderivatives of the same function. All right, moving on to part 3, the power of differentials and Leibniz's winning notation.
This notation is so incredibly powerful, it actually helped Leibniz's version of calculus beat out Newton's across Europe. The British mathematician Bertrand Russell once noted that calculus required continuity, and continuity was supposed to require the infinitely little. And that philosophical challenge, the infinitely little, is exactly what differentials capture. When you write dy over dx, we're not just scribbling a symbol for a derivative. Leibniz viewed this as a literal ratio of infinitesimals. And geometrically, this is fascinating. dy and dx aren't just shorthand. They are tangible horizontal and vertical steps on a tangent line that approximate our curve. While delta y and delta x represent the actual finite change on the curve itself, dy and dx represent the change if you went straight up the tangent line. The big takeaway here, by treating dx as a tangible mathematical object, like a real number we can actually divide or multiply by, linear approximations and related rates become a completely logical algebraic exercise. We can write things like dy equals the derivative of f of x times dx. That's a totally coherent way to manipulate equations without even having to specify what your independent variable is yet. It's a real game changer. Part 4, substitution made simple. By applying these differentials, let's see how this maps out practically. Because, let's be honest, while differentiation is mostly just a mechanical process of applying rules, integration can be notoriously difficult. Sometimes it's literally impossible. So when faced with a terrifying integral, we use substitution. And substitution is tailor-made for Leibniz's differential notation. You just identify the messiest inner function, let's call it u, then you take its differential, du. Since we're treating dx as a tangible quantity, we can literally swap out the messy x terms and the dx for clean, simple u terms and du. It seamlessly transforms an unsolvable nightmare into a basic power rule problem.
Which brings us to part 5, bridging area and distance, the grand unification. This is the climax of the explainer. We've got these abstract algebra rules, but what do they give us in the real world? Let's ground this. Imagine tracking a train over time. At time 0, it starts moving. As the hours pass, it accumulates distance. If you were to graph that train's velocity over time, the total distance it traveled is exactly equal to the total area accumulated under that velocity curve. Geometrically, imagine that area accumulating. As our x value increases, the right wall of this shape moves outward, sweeping out more and more area. Now, how fast is that area growing? Well, the rate at which the area increases is exactly equal to the height of that right wall, which is just the value of the function itself. And that leads us to the absolute core of the subject, the fundamental theorem of calculus. The instantaneous rate of change of the area under a continuous curve equals the value of the curve itself. This is stunning. It elegantly connects the concept of finding an area under a graph directly to the antiderivative we talked about at the very beginning. To find the area, you just find the antiderivative, plug in your endpoints, and subtract. It's an absolute masterclass in unifying rates of change with accumulated area. I really hope this structured look at calculus leaves you seeing it not as a set of frustrating rules, but as a deeply logical system. By reading our formulas backward, embracing the ambiguity of that constant c, and leveraging the sheer power of differentials, we unlock the geometry of the physical world. So I'll leave you with this. If integrals can perfectly reverse engineer derivatives to reveal hidden areas and distances, what other hidden physical realities can calculus unlock for you? Keep exploring, and I'll see you in the next explainer.